Okay, good morning. Listen, today's concepts, almost electronic portion that we have covered. Okay, another important concept that I supposed to cover it today. One more important idea. Okay, before that, taking up the important concept, one more question first I supposed to teach. We are asking for 1 mark. What is that? We are asking for 1 more question as define dynamic resistance of a junction diode. We are asking. Define dynamic resistance, AC resistance. Define dynamic resistance of a diode, of a junction diode. We are going to ask. This carries 1 mark. Define dynamic resistance of a junction diode. Okay. Already we are aware of PN junction, how it is going to get working and other things. Practical concept also I taught already. If there is a change in the voltage, there is a change in the current. As you are plotting a graph, forward bias. This is forward bias characteristics. This is the voltage and this is the current in terms of milliamps. Then you are going to get the points like this. You will get the points like this. If you are joining all these things, this is called by the name the forward bias characteristics. Practicals. Under practicals, you are going to draw all these things. Now, if I'm drawing a small a triangle here, a small triangle where the straight line portion is there only we are supposed to draw it, not at the curve region. Because Ohm's law is not holds good for the curves. Ohm's law is holds good only for the straight line graph. Now, this is delta I here, means this point to this point. This is delta I, this is I, this is delta I. According to mathematics, delta I means is a small current. This is V here, this is delta V. Now, a small change in the voltage, there is a small change in the current. The ratio between the small change in the voltage to the small change in the current, the ratio between the small change in the voltage to the small change in the current, this is called by the name the dynamic resistance. Either you can write small r suffix d or you can write capital R suffix d, no problem. Resistance, dynamic resistance. Define dynamic resistance of a diode. Dynamic resistance of a diode may be defined as, for a small change in the voltage, there is a small change in the current. For a small change in the voltage, there is a small change in the current. The ratio between the small change in the voltage to the small change in the current, this is whatever we have applied, this is whatever we have observed. So whenever if you are changing some amount of voltage, there is a small change in the current. The applied voltage is delta V. The change in the current is delta I. The ratio between this voltage to this current is called by the name dynamic resistance of a diode. In the notes is not properly mentioned. Be careful. Notes, there is a mistake. It is the ratio of the small change. It is the ratio of the small change in the applied voltage delta V to the change in the current delta I is called by the name dynamic resistance of a semiconductor diode. This is called by the name the dynamic resistance of a semiconductor diode. Okay, this is for 1 mark question. Now, today's concept for about 3 marks question. Before that, again 1 mark question we are asking. Again, we are asking for 1 mark question. What is that 1 mark question we are asking here? First 1 mark question. What do you mean by a Zener diode? We are asking. What do you mean by a Zener diode? Zener diode to ordinary diode, what is the difference? Zener diode means what? Zener diode means the diode in which we are going to dope, means doping means addition of impurity. The addition of impurity is said to be more here. Percentage of impurity atoms are more. Hence, conduction is also more. Free electrons are more. Therefore, Zener diode is a specially made device where it is said to be heavily doped junction diode. Basically, this is heavily doped junction diode, nothing else. It is also a junction diode. Zener diode means nothing else. Zener diode is also a junction diode, but it is heavily doped. An ordinary diode is not heavily doped. We are doping in the form of, in the ratio of 10 to the power 8:1. Then it is an ordinary diode. As you are adding the impurity atoms more and more here, addition of impurity is called by the name the doping. A heavily doped semiconductor diode, a heavily doped junction diode is called by the name the Zener diode. Zener diode, most of the occasions, 99.9% of occasions, we are using only in the case of reverse bias. We are not using in the case of forward bias. If you are using in the case of forward bias, 10 to the power 8:1. You read the notes, you will get all the information. Doping level 10 to the power 8. 10 to the power 8 germanium atoms. One atom we are adding the arsenic or maybe the trivalent impurity that we are adding. Zener diode is not like that. We are not adding one atom. 10 to the power of 8 germanium atoms are there. One atom is we are not adding. We are adding more than this. Then only it is called by the name the Zener diode. Addition of impurity is said to be more. Heavily doped junction diode. Heavily doped junction diode is called by the name the Zener diode. Now, in the case of Zener diode here, we are connecting the Zener diode only in the form of reverse bias condition. Reverse bias condition, it will work for a long time interval without spoiling. Zener diode is not going to get spoiled. It's going to get work for a very lengthy time interval without getting damage. Without getting damage, it will work for a long time interval under reverse bias, but I'm not sure to say that one. Even for about 5 minutes, it will not work under forward bias because the current flow is more, it cannot tolerate. And the application of Zener diode is present in the reverse bias only, not in the forward bias. The application of a Zener diode is present in the form of reverse bias, but we don't have any applications of Zener diode in the form of the forward bias. Forward bias, it will not work for a long time, but reverse bias, it will work for a very lengthy time without any damage. So without any reverse effect, without any amount of spoiling effect, the Zener diode, it will work for a lengthy time interval in the form of reverse bias. We have to think about reverse bias condition of Zener diode only. Then the next case, how we are going to write this Zener diode symbol. One more question. All these concepts we are asking for one more question. So I told you already, define dynamic resistance of a diode. In the case of an ordinary diode, for a small amount of change in the voltage, whatever we have applied, there is a change in the current here. The change in the voltage to the change in the current, that ratio is called by the name the dynamic resistance. Zener diode means a heavily doped ordinary junction diode. For an ordinary junction diode, if you are adding the more amount of impurity atoms here, then I can say it is called by the name the Zener diode. Zener diode, it will work for a lengthy time interval in the form of reverse bias, and more applications are there in the form of reverse bias. You are going to study only one application. Then, how we are writing the symbol for Zener diode? Zener diode, how we are going to show this symbol? So ordinary diode, we are writing the symbol like this. This is ordinary diode. All of us already we are aware of this. This is a diode. This is a diode where this is P and this is N. This arrow mark representing the P, the line representing N. This is the PN junction. Then this is the symbol for ordinary diode. Now I will write the Zener diode here now. The Zener diode symbol, how we are going to write the Zener diode. The Zener diode symbol, we are going to show it like this. This is a Zener diode symbol. If you are writing this much, You will get 1 mark. So how we are going to write the Zener diode symbol? The Zener diode symbol is said to be like this. This is Zener diode symbol. Okay, Zener diode symbol. If you are writing like this here as a N variety, P as it is, if you are writing, you can say it is said to be a Zener diode. It is a Zener diode. So Zener diode we are going to mention like this for 1 mark question. Write the circuit symbol for Zener diode. This is a circuit symbol for Zener diode. If you don't mention like this, okay, it is an ordinary diode. Now, today's very important concept for about 3 marks. We are asking for 3 marks. Explain Zener diode as a voltage regulator. We are asking for about 3 marks question. Zener diode as a voltage regulator. Voltage regulator. Explain the action of a Zener diode as a voltage regulator. This is a question. Explain with a necessary circuit diagram the Zener diode acting as a voltage regulator. Very easy concept. Very easily we can understand all these ideas. This usually we are asking this question for 3 marks. Okay, for 3 marks question we are asking. Then how it is said to be dividing the marks? Circuit diagram carries 1 mark. Output input carries 1 mark. Explanation maybe carries 1 mark if they are asking for 3 marks. If they are asking for 5 marks, explanation carries maybe 3 marks. The circuit diagram carries 1 mark. Output and input characteristics carries 1 mark. Okay, first idea, the circuit diagram. How we are going to show the circuit diagram for the Zener diode acting as a voltage regulator. Okay, this is a Zener diode, I told you already, and we are supposed to connect it in the form of reverse bias only. Zener diode must be connected in the form of reverse bias only. Okay, unregulated voltage supply means DC voltage only, but voltage is not a constant voltage. Voltages go on increasing, decreasing, increasing, decreasing like this. Polarities remain same. Polarities remain same here. Same kind of polarity is present. It is passing in the same direction. But voltage is not a constant. Constant voltage is not present here, but voltage is a variable. The variable voltage source is called by the name unregulated voltage source. So here I will going to connect like this. This is a copper wire. This is a resistance. Resistance, we are supposed to show it like this only. This is the resistance. I will write this one as R suffix S because they are connected in series. S representing for series. It is a load resistance, series connection, dropping resistor. This is also called by the name the dropping resistor. And then we are connecting here. We are connecting here. A Zener diode we are supposed to connect. This is a Zener diode. This is a Zener diode. This Zener diode, P variety, I will connect like this. This is a P variety. This is Zener diode, P variety. Okay. Switch off your, this is Zener diode. If you are waking up now only, I cannot help you. This is Zener diode. Okay, this is a load resistance. I will connect here. This is a load resistance. If you miss the classes, no problem. Evening 6:30, 6:40, you switch it on. 6:30 only. Some occasion that I will going to start late. Okay, this is the output voltage. It is evening 6:30, you will wake up now, no problem. Morning 8 o'clock, you may not wake up because it is very early now, 8 o'clock. Okay, this is a connection here. We are supposed to connecting here as a DC source only that we are supposed to connect. This is N variety. This is N, this is P. This is N and this is P. P must be connected to the negative end here. N must be connected to the positive end. This is positive end. This is negative end. Like this. This is negative. This is a variable voltage source. Don't forget. We are supposed to connect it practically. It is a variable voltage source. I can say it is unregulated DC voltage, V input. This is unregulated DC voltage. This is V suffix input, V in, I will write. This is V suffix in. This is unregulated voltage, means voltage is not a constant. Voltage regulator means you are aware of that voltage regulator. At home also we are using for the TVs and other things. Inbuilt regulators are there, voltage regulators. Okay, that idea that we are going to show it in the case of practicals here. Then whatever the current that is flowing here, it is said to be taken as IZ. This is said to be taken as I suffix Z. IZ current. Here the load resistance is present here. This is a load resistance. I told you already, load resistance means a large resistance that we are connecting. The current, whatever it is flowing through here, it is called by the name the IL, load current. Here you are going to get the regulated voltage. This is the regulated voltage. You are supposed to get it here. If you are connecting a voltmeter here, if you are connecting a voltmeter, you are going to get here regulated voltage. Regulated voltage represented by V output, V naught or V output. If you are writing this much, you will get 1 mark for this. Circuit diagram carries 1 mark. Zener diode is there. Zener diode, this is Zener diode. The Zener diode, you see that symbol, the Zener diode. P variety must be connected to the negative end. N variety must be connected to the positive end through a resistance RS. Through a resistance RS. Through a resistance RS. This RS is called by the name dropping resistor. This is called by the name dropping resistor. Dropping resistor. Because voltage is going to make a drop here. It is called by the name the dropping resistor. This is load resistor. This is a load resistance, a load resistor. Here we are getting an output voltage that is said to be the regulated voltage. Now how it is said to be working? Very easy concept, how it is working. For every Zener diode, there is a Zener breakdown voltage. You are aware of Zener, breakdown voltage, you are aware of that. So for every breakdown voltage here, as the voltage increases further, current only it is going to make it increases, but not the voltage. Voltage never increases. I think I have shown it already in the case of the diode voltages. Okay, as the voltage is go on increasing. Oh, yes, somewhere else is there, you just go through that. So Zener, let us consider for a Zener voltage. For an example, I will going to consider only for an example here. For Zener voltage, for Zener diode, let us consider. For a Zener diode, there is a breakdown voltage, V suffix break. There is a breakdown voltage. And in the market, Zener voltage, whatever the breakdown voltage is there, Zener breakdown voltage, it is available in the market with different values. 8 volts Zener voltage. If you are going to the KT Street and if you are asking for a Zener diode, he will ask first, okay, how much is the breakdown voltage? The breakdown voltage is available with 6 volts, available with 8 volts, available with 11 volts, like that. Okay, so anyhow, let us consider as an example here, this V break, let me consider it is equal to 5 volts or 6 volts. Breakdown voltage is equal to 6 volts. What is that meaning here now? What is that breakdown voltage is equal to 6 volts? Meaning, across this one, the voltage we can maintain up to 6 volts, no problem. After 6 volts, it will not increase the voltage. Here, across this one, voltage never increases above 6 volts. Even though you are increasing the voltage here, across this one, voltage is go on increasing up to 6 volts. Further, 7 volts you will not get here. 8 volts you will not get here. Here you will get only 6 volts. For example, here if I am applying 1 volt, here if I am applying 1 volt, whatever we are applied, unregulated voltage supply, 1 volt if we are applying here, that voltage is dividing here also and here also. Here some voltage, here some voltage. Voltage of this and voltage of this one, if you are adding these two voltage, addition of these two voltage, this voltage, across RS, across Zener diode, across RS, whatever the voltages are present here, if you are adding these two voltages, it will be equal to the applied voltage. Across RS, across VZ, whatever the voltages are present here. Now, if you are adding these two voltages, you will get this voltage. Now, as you are increasing the voltage here, here also voltage increases, here also voltages go on increasing, but these two are sharing the voltage. They are dividing the voltage. Up to what? Up to 6 volts here. For example, let us consider here we are applying 10 volts. As you are applying 10 volts here, this may be taken as 4 volts, depending upon the resistance value. 4 volts. Don't say that one. Why it is taking 4 volts only? Why can't it take it as 6 volts? It can, depending upon this resistance value. So now anyhow, we are applied 10 volts here. Here it is taking up 4 volts. Remaining 6 volts is present here. 6 volts is present here. 4 volts is present here. 4 plus 6 is equal to 10. If I'm applying 11 volts here, now here 6 volts only, because it is breakdown voltage 6. 6 volts only it is present. Remaining 1 more volt that is taken up by the RS. 5 volts is present here. Instead of 4, it will take the 5 volts. Voltage drop. That's why it is called by the name the dropping resistor. Across this one, there is a voltage of 5 volts. Across this one, voltage is equal to 6 volts. 6 volts plus 5 volts is equal to 11 volts. If you are applying 12 volts here, here it is 6 volts only, but here it is said to be equal to 6 volts, increases to 6. If it is 15 volts, if you are applying, here 6 volts only, but remaining 9 volts it is coming here. Therefore, whenever 6 volts only is present here now, if these two are connected in parallel here now, whatever the voltages are present here, the same voltage is also present here, because these two are connected in parallel. Under electricity, I will explain if the two resistors are connected in parallel. This is also having a resistance. If the two resistors are connected in parallel here, voltage remains same. Here if it is 6 volts, here also 6 volts, here also you will get 6 volts. Now what is happening here? As you are applying 10 volts here, here there is 4 volts, here 6 volts, here 6 volts, therefore voltage is showing as 6 volts. If it is applied 15 volts here, if we are applied 15 volts, here it is 6 volts, here it is 9 volts. I'm not bothering about this, but here it is 6 volts, here it is 6 volts, here also 6 volts. So voltage is changing here, applied voltage is changing, but here the voltage remains same. That's why it is called by the name voltage regulator. This idea in larger quantity we are using in the case of factories, homes and everywhere. In your home also, voltage regulators are there. Voltage regulator, whenever if you are connecting to your what is that, TV or maybe the music system or something else, then the kV current or the voltage supply, kV voltage supply, if it is varies here now, then the Zener voltage remains constant. Then the remaining voltage will be taken up here. Whatever we require, that voltage remains same here. Therefore, it is acting as a voltage regulator. Now, again, I will repeat the concept just to see that two concepts are there here. As the voltage increases, unregulated DC voltage, input voltage, as you are increasing, then voltage drop across the Zener diode remains same. Therefore, across RL, voltage remains same. Extra voltage is taken up by the RS. As you are increasing the voltage across RL, across RS, voltages go on increasing. But across RL, voltage remains same. Because voltage across the Zener diode remains same, voltage across RL remains same. So I will write that point here, point number 1. Okay. Above V break. Above V break. If the applied voltage increases, above this breakdown voltage, here if you are increasing the voltage, then what is happening? Across Zener diode, I can say VZ, this is voltage across Zener diode is VZ. Then across Zener diode, voltage remains the same. Voltage remains same. How much it is the voltage remains same? 6 volts only. That is your VZ. Voltage remains same. That is 6 volts only. Example, 6 volts. But extra voltage taken up by the RS. But across RS, the voltage increases. The voltage increases across RS. Across RS, voltage increases. Across Zener, voltage remains same. Therefore, here the voltage remains same here. As the voltage remains same here, across RL also voltage remains same. Therefore, across RL, voltage, output voltage does not alter. Does not alter means it remains same. This is voltage regulator. This is point number 1. Above the breakdown voltage, above this breakdown voltage, as you are applying the voltage more and more here, across this one voltage remains same, across this one voltage remains same, extra voltage is taken up by this RS. For example, if breakdown voltage is 6 volts here, if you are applied 10 volts here, here it is 6 volts, here it is 4 volts. Here it is 6 volts, here it is 6 volts. If you are applied 15 volts here now, here it is 6 volts, here it is 6 volts, here it is 6 volts. But here 9 volts. If you are applied 20 volts here, here it is 6 volts, here it is 6 volts, here it is 6 volts only. But 14 volts is present here. Extra voltage will be taken up by this RS. This is above breakdown. Lesser than breakdown, what will happen? Means above the breakdown only, as the applied voltage increases, I said here. Here I have written applied voltage increases. Now we're going to take above the breakdown voltage, if the applied voltage decreases. What will happen? Similar way, same concept, 20 volts. Here it is 6, here it is 14. Here it is 6, here it is also 6, here it is 6 volts, here it is 14 volts. Now 20 volts, I will reduce us to 10 volts. 14 volts reduce us to 10 volts now. 20 volts reduce us to 10 volts. If 20 to 10 volts, if I'm reducing here, decreasing here, instead of increasing, decreasing here, now here it is 6 only. Here it is 6, here it is 6, but here it is 4. I hope you understood. If it is 20 volts present, here it is 6, here it is 14. Here it is 6 volts and 6 volts. If it is 15 volts is present, 20 to 15 reduced, then here it is 6 only. This is 6, this is 6. But here 9 volts is present. 9 plus 6 is equal to 15. So therefore, I can say above the breakdown voltage, if the applied voltage decreases, then across Zener diode, voltage remains the same, VZ only, but across RS, the voltage decreases. Therefore, across RL, output voltage does not alter. Therefore, it is acting as a voltage regulator. Shall I write that one also, just to see that? I will write that concept also. Still 6 minutes time is there, no problem, I will write. Okay, followed this concept, right? Before that, you are supposed to write here one thing. The circuit is as shown in the figure. Okay, the circuit connection is as shown in figure. Write that much, enough. This carries 1 mark. Explanation carries maybe 1 mark, 2 marks question, 2. Okay, output characteristic also we are supposed to write. I will write the same concept, but in a reverse way now. So what is that? I will show that also, just to see that what I am writing here and what it has been already written. Okay, point number 2. Above we break. Above the breakdown voltage. Above the Zener breakdown voltage. If the applied voltage, decreases, then across Zener diode, voltage remains same. Voltage remains same. How much it is? Vz only. How much it was? Example, 6 volts only. 6 volts only. But across RS, the voltage decreases. Here, if it is increases, across RS, the voltage is go on increasing. Applied voltage increases, across RS, voltage is go on increasing, but across Zener diode, voltage remains same. Here, above the breakdown voltage, if the voltage decreases here, applied voltage decreases. As the applied voltage decreases here, then the voltage remains same here now across the Zener diode, but across RS here, the voltage decreases. But therefore, across RL, this is load resistance, this is the dropping resistance. So across RL, there is a constant output voltage. Output voltage does not alter. As the output voltage does not alter, I can say V output remains constant. If it is constant, I can say it is Zener diode as acting as a voltage regulation. Voltage regulator, it is acting now. We are supposed to show with a graph also. What is that graph? Input versus output voltage. V input, this is V output. As you are increasing the V input here, output is also go on increasing, up to a particular limit. Then further, the voltage, input voltage as you are increasing here, then the output voltage remains constant. Output voltage remains constant. This is your Vz. This is your Vz value. This is Vz value. I shown that Vz value is equal to 6 volts there. This is Vz, breakdown voltage. Up to breakdown voltage, across Vz also it is go on increasing. RS versus Vz also is go on increasing. But after Vz is present here, as the input voltage increases, across the across the Zener diode, voltage remains same. This is called by the name voltage regulator. This is called by the name the voltage regulator. I will show both the concepts. This is a circuit diagram and other things. If you are writing this much is enough. In the notes that I have given with the bold letters, whatever it is given with the bold letters, if you are writing that much is enough. The other things for the explanation purpose, it has been given. Otherwise, only the bold letters, if it is given in the notes, we cannot understand. If you are reading the notes, you cannot understand. Okay, therefore, it has been given little bit more ideas are given. If they are asking for 3 marks question, you write the notes, whatever I have sent now, just you write with the bold letters, whatever it has been printed. Just you write. Otherwise, you write this much only, no problem. If you are writing this much is more than enough. Not only this, this also. Graph also I have to show it. Evening 6:30, 6:40 like that. Again, I will show all these concepts. Anybody wants to have, you can admit and you can see that. A very important concept. Okay. Explain the Zener diode acting as a voltage regulator for 3 marks question. Usually we are asking for about 3 marks question. I think practicals also you are having this.